Welcome. Welcome to our self-study online training for Lean Six Sigma Yellow Belt training. This class is all about statistical approach. The first one, statistical meaning of sigma. Sigma is standard deviation of process for a given property. Standard deviation means indicator for what data is scattered much from the average. From the average, how it's scattered. This data is applicable for numbering of variation by centering of average, which the specific process or product property have. Now see, property of data. The first is about the center. There are mean, median, and mode. Mean, arithmetic mean for a set of values, but unfortunately is related heavily influenced by extreme value. We call it this one outlier. So mean can be affected by some of outlier. So in that case, we use median. Median is number representing the order of 50% of the data. When you line up the data, when you sort it, the middle of the data, we call it median. This is not affected by extreme value. This is not affected by outliers. The mode, the value that occurs mostly frequently in a series of data. So this one represents about the center.
Okay, so welcome to my first video on statistics. In this video we're going over the mean, median, and mode, the three central tendencies, the foundation of statistics. And it's really important that you understand these core concepts because you're going to use them throughout the duration of your course. So let's get started right away with an example, and hopefully this will all make more sense after we're finished. Now let's say we have the numbers 10, 20, 30, 40, and another 40. And we need to find the three central tendencies of this data set, so the mean, median, mode. So let's start out and let's find the mean. The mean is more commonly known as the average, so we need to find the average of these set of numbers. And in order to find the mean, you just have to add all the numbers. So let's add all our numbers. We add 10 plus 20 plus 30 plus 40 plus 40, and then we need to divide by the total amount of numbers. We have 1, 2, 3, 4, 5 numbers in our data set. So we need to divide by the number 5. And if we add 10 plus 20 is 30, 30 plus 30 is 60, 60 plus 40 is 100, 100 plus 40 is 140. So in our numerator, we have 140, and in our denominator, we have 5. 140 divided by 5 is equal to 28. So our average, or our mean, of this data set is equal to 28. Alright? So now let's find our median. The median can be found. First, what you need to do is order the numbers from smallest to largest. And this is already done. We have 10, 20, 30, 40, and 40. So they're already from smallest to largest. And the median is always the number that's right in the middle. Notice how this number 30, we draw a line through it, how there's two numbers to the left of 30, and there's two numbers to the right of 30. So 30 is the number that's exactly in the middle. So our median is equal to 30. And just a quick side note, the median is a little different if you have an even set of numbers. Let's say we had the numbers 10, 20, 30, 40, 50, and 60. Notice how now that instead of having 5 numbers, now we have 6. And if we drew a number, or if we try to find the number that's right in the middle, we have it's in between the 30 and the 40. Notice how there is 3 numbers to the right of the line, and there's 3 numbers to the left. So whenever this happens, you take the 2 numbers that are in the middle, 30 and 40, and you average them together. So 30 plus 40 divided by 2 is equal to 35. Alright, so for this particular data set, the median is equal to 35. Alright, so let's go back to our original example. Alright, so we found our mean, we found our median. Now let's find our mode. Our mode is just the number that occurs the most. And I'll circle the number that occurs the most in red. Notice how every number occurs once except for 40. We have 2 40s. So because 40 occurs the most, our mode is equal to 40. So now we have found all our measures of central tendency. Our mean is equal to 28, our median is equal to 30, and our mode is equal to 40. So many people ask me the question, what is the best measure? Is the mean better than the median? Is the median better than the mode? Which measure of central tendency should we use, the mean, median, or the mode? And I don't have an exact answer to that question. You probably should just use your common sense. This will make a lot more sense if I just use an example. Let's say, for example, that you're measuring your weight. And every day, every morning, you go on a weight scale and you measure your weight. So let's say one day you measure yourself and you weigh 100 pounds. And then the next day you measure yourself and once again you weigh 100 pounds. The next day you weigh 100 pounds. Fourth day you also weigh 100 pounds. And let's say on the 5th day, let's say you weigh, let's just make it really ridiculous. Let's say you weigh 600 pounds on the 5th day. Alright, now, if we found our mean for this set of data, it would be 100 plus 100 plus 100 plus 100 plus 600 divided by 5, and our mean would be equal to 200. Now the median of this data set is just the number that's right in the middle, which is 100. So our median is equal to 100, and our mode is also going to be equal to 100 because the number 100 occurs the most. And I think it's pretty common sense that the median and the mode are much more accurate measures of central tendency than the mean. Okay, that is because this number 600 is obviously inaccurate. There must have been an error in the weight scale, or there must have been some sort of error. There's no way you can gain 500 pounds in one day, and that really affected our mean. Our mean, you know, obviously your weight is around 100 pounds, and the mean says that your weight is the average is 200 pounds. So that's not even close. The mean is probably not a measure of central tendency that you should use, and the median and the mode are much more accurate descriptions of this data set. So use your common sense. I hope you enjoyed this video and this gave you a better idea of mean, median, and mode. I will be making a video on standard deviation next, so stay tuned.
Okay, we can see clearly about the mean, median, and mode. Please remember, if there are some outliers which affect to the center, then much better we use median. So this is case study. This is data set. So mean is just sum of it and divide by number of data. What will be median? Let's think about it. And what is mode? First, median. Let's see how many data here. This data set has 10. And the middle is this 5 on the left, 5 on the right. So this one, median is average of 5 and 6. So the result will be 4.5. The median is 4.5. And mode is 3. Frequently appears number 3. So mode is 3. And now we study about variation. Variation, the representatives of variation is range, variance, and standard deviation. The first, range, the difference between the maximum and minimum value. So simply, maximum minus minimum is the range. The simplest and most simple way. But it's not reflecting the size of each data. We can see only the data range from the maximum to minimum. Variance, average data from scaling differences between average and individual data. And this one reflecting the size of each data. There are the population variance and sample variance. That's why this is population variance, this is sample variance. Standard deviation. This is the square root of the variance. Square root. The most commonly used method for quality of variation. Because when you handle the data set, not only 10 or not only just 100, like a millions or thousands, millions, in that case variance is too big, huge number. So we prefer minimize it. So we use it standard deviation. Let's see more.
Hi guys, welcome to our section how to find the range, the variance and the standard deviation of the sample. Let's start. First of all, what is the range, the variance and the standard deviation? These are just measurements of dispersion. They just tell me how spread out is my data. Let's see an example. Let's say that you have this data, 3, 3, 3, 3, 3, 3. See here that everyone is the same, so there's actually no dispersion. But what happens if I have something like this? 3, 10, 11, 17, 19, 10,000. Well, in this case, I can see that my data is not the same, and there is actually dispersion. So how do I measure that? Well, we're going to measure it by learning the range, the standard deviation, and the variance. Let's start with the range. Let's say they ask you to find the range of the following data. Well, the range is very simple. It's just the largest values minus the smallest values. For example, if I have something like this, which will be the largest value? In this case, I have 5, and the smallest one is going to be 1. So my range is going to be 5 minus 1, which is equals to 4. Beautiful. It's very simple. Let's do now the variance. The variance has this nasty formula, which is equals to the sum of x, which in this case, x is going to be 1, 5, 4, and 2, minus the mean. X bar means the mean, or the average, all that to the square, divided by how many items I have, in this case 1, 2, 3, 4, minus 1. Let's do it step by step. The first thing, let's find the mean. I go 1 plus 5 plus 4 plus 2 divided by 4 because I have 4 items. 1, 2, 3, 4. Let's do it. 1 plus 5 is 6. 6 plus 4 is 10. 10 plus 2 is 12. 12 divided by 4 is equals to 3. Beautiful. Second step. Once you have your mean, which is actually 3, you're going to go ahead and do every single x value minus the mean, and then you're going to square it. For example, 1 minus 3 is equals to negative 2. But when you square negative 2, what do you get? You get equals to 4. Plus 5 minus 3 is also negative 2. But negative 2 times negative 2 is also equals to 4. 4 minus 3 is equals to 1. 1 times 1 is 1. I'm almost done. And then 2 minus 3 is equals to negative 1. Negative 1 times negative 1 is just 1. Finally, I just add 4 plus 4 is 8, plus 1 is 9, plus 1 is 10. Beautiful. Now that you have this, we're going almost to the last step. I divide all that, which all this is represented here, divided by n, which is 1, 2, 3, 4, minus 1. I get that my variance is equals to 10 divided by 3, which I get this really nasty number, 3.33333 to the n. Now, let's do the standard deviation. It is the same thing as the variance. Look, it's almost the same formula. However, I need to square root whatever answer I get. Do you remember how we got 3.3333? Well, in order to find the standard deviation, I just need to do the square root of the value, which is equals to 1.83. Let's do another one. Again, find the range of this data. Remember, the largest one minus the smallest one. 9 minus 0 is equals to 9. So easy. Now let's do the variance. Again, first step, find the mean. I go 3 plus 7 plus 9 plus 1 is equals to what? 3 plus 7 is 10. 10 plus 9 is 19. 19 plus 1 is 20. 20 divided by 4 is equals to 5. I got my x bar. Now we're going to subtract every single value minus the mean, and we're going to square it. Let's do it. 3 minus 5 squared is equals to negative 2. Negative 2 times negative 2 is 4. Plus 7 minus 5 is 2. 2 times 2 again is 4. 9 minus 5 is equals to 4. 4 times 4 is equals to 16. Almost done. 1 minus 5 is negative 4, but negative 4 times negative 4 is also 16. When I add 16 plus 16 plus 4 plus 4, that's equals to 40. And the last step, count how many items you have. 1, 2, 3, 4. I do 40 divided by 4 minus 1, which is equals to 13.3333. Finally, once you have your variance, in order to figure out your standard deviation, remember, you do the same thing. Do the whole thing. Once you get this value, just find the square root, which is equals to 3.65. I'm going to recap. If you have the variance, the square root of the variance is the standard deviation. If I actually have the standard deviation and I want the variance, the only thing you have to do is plug this value in your calculator, do the square of that value, and you get this baby, 13.3333. They are a pain in the neck to calculate. This is why sometimes we do the standard deviation and the variance in the calculator. So please go ahead and watch our videos how to figure it out, the standard deviation, the variance, and every single thing in the calculator in our channel. Again.
Okay. Let's set defects and defective product. What is different defect and defective? Defect is number of failures per unit. What is unit? Unit is quantitative measurement of each area researched. Can be observation and quantification. It will be based on counting defects. So simply in manufacturing company, if we produce product or WIP, work in process, that will be unit. Let's go back to defect. If a unit is to be turned out to be defective, there exists more than one defective. This one causes customer dissatisfaction. The thing cannot match to specified criteria, like a specification. So no matches of standards to meet the customer requirements. So we have to meet standard so we can meet customer requirement. So this is a defect. What is defective? Defective is the finished product judged by NG. Defective product per unit. First pass yield, number of non-defective unit. This one is the number of good product divided by total unit. And now we'll study about DPU, DPO, DPMO. DPU is defects per unit. DPO defects per opportunity. DPMO is defects per million opportunity. Opportunity means the number of opportunities that may arise from defects. So let's see what is DPU, DPO, and DPMO, how calculated also.
To calculate the defects per million opportunities, or DPMO, divide the number of defects by the amount of units times the amount of opportunities, and then multiply that total by 1 million. Keep in mind that one unit can have multiple opportunities. For example, a form, the one unit, contains 10 fields of information. So each form has 10 potential opportunities for an error. If 5 forms are sampled and 12 defects are found in the sample, the DPMO is 12 divided by 5 times 10, which equals 24, times 1 million, which comes to 240,000. Another alternative is to measure the defects per unit, or DPU, which yields the average number of defects per unit. To calculate the DPU, divide the total number of defects found in a sample by the sample size. And finally, parts per million, or ppm, is a very common metric which is used in production environments. ppm is similar to DPMO, except that instead of measuring defects based on the amount of opportunities, defects are measured against the whole part or service. An item is said to be defective when the decision is made that the item is not acceptable, based either on one characteristic or the accumulation of multiple characteristics. This means that a sample of 100 units can only yield a maximum of 100 defective units. To calculate the ppm, divide the number of defective units found in a sample by the sample size, and then multiply that by 1 million. Let's use penny production as an example. The total number of pennies is 20, and if there are 5 pennies deemed to be unacceptable, the ppm would be 5 divided by 20 times 1 million, which comes to 250,000 pennies per million opportunities. The DPMO digs a bit deeper to understand out of those 20 pennies how many opportunities there are for nonconformance and how many defects were found. For a penny, the opportunities are color, shape, brightness, lettering, feel, and the image stamped on the penny. This means that every single penny could potentially have 6 defects. Or, in other words, more than one defect can be found for each penny. If you found 26 defects in the 20 pennies, the DPMO would be 26 divided by 20 pennies times 6 opportunities multiplied by 1 million, which comes to 216,667 defects per million opportunities.
So let's check this one again. DPU, the number of defects per unit. So when you calculate it, we count first total defects and then divide by total units. Remember, DPU is only about the defect divided by unit. DPO is total defect divided by total opportunity. For example, in one unit, it can be one opportunity, but mostly it has more than one, multiple opportunities we have. Like a previous video in penny, yes, there are 6 opportunities for 1 penny. And DPMO, yes, this one is just a million opportunity from DPO. The opportunity is the one we choose as an inspection criteria. So this is the case study. When we inspect product 100 pieces for the performance testing of new equipment in manufacturing processes, 20 defects appeared from 100 pieces. Here is defect, here is unit. 1 defect from 1 product, 2 defects from 8 products, and 3 defects from 1 product. Inspection item are 4, meaning, for example, color, measurement, density, and weight, like that. So this one inspection item is opportunity. So DPU we calculate how. Unit is 100 here. Defect here. Defect per unit DPU is 0.2. DPO defect divided by opportunity. So opportunity is for one piece. Here 100 pieces. So total opportunity calculated by 100 times 4. So 400 opportunities. So DPO is 0.05. DPMO is just DPO times 1 million. Let's wrap up about DPU, DPMO, and DPO. Unit is number of products subjected to the test. Defect, detecting the number did not pass the specifications in product. The total sum of the number of defects equal number of defective products in the inspection. Opportunity inspection items per unit product. Total number of opportunities equal unit times number of opportunities per unit. Why we should calculate DPMO? We can check our sigma level through DPMO. We can notice our current level through Six Sigma level. We can notice opportunities for improvement and current COPQ approximately. Okay, this is DPMO and sigma level comparison. This is DPMO, this is sigma level. So Six Sigma level is 3.4 DPMO. Normally, local company, the level is almost 3 Sigma level. DPMO is 66K800. So when you convert it to yield percentage, this one is 93.3.2%. 93.32% is the average of the manufacturing company in local, not the global company. And the relation with DPU and COPQ, when DPU increase, also COPQ will be increased. It's natural. So once DPU reduce, COPQ also will be reduced. And now see the relationship among CTQ, CP, and COPQ. CP versus CTQ proportional relationship. Once CP level up and CTQ also level up. But CP and COPQ inverse. Once CP increase, COPQ will be decreased. CTQ and COPQ is the same inverse. And now we study about VSM, value stream map. Value stream map is coming from Lean. The value stream is an entire set of processes or activities performed to transform the products and services into what is required by the customer. That's why we put value, because value is coming from customer. Supplier, from the supplier, design, procure, produce, and sell to the customer. The primary focus is time. And this left to the right is product or service flow. Information flow in all directions. Let's study more VSM, value stream map.
Welcome to Vlaction Continuous Improvement's presentation on value stream mapping. I am Jeff Hajek, the owner and founder of Vlaction. We've got a few basic objectives on what we'd like you to take away from this training. First, we want you to walk away knowing what a value stream map is and what it is used for. On top of that, we want you to see the value in this extremely important tool. Second, we want to teach you the basics about creating a current state value stream map. You won't get good at value stream mapping until you've done it a few times. Our goal of this video is to get you comfortable enough to go out into your production areas and start putting pencil to paper. Now, it would be rather difficult to create a value stream map if you didn't even know what a value stream is. So let's start out by addressing that question. In a nutshell, a value stream is the series of activities that you have to do to provide a product or service to a customer. There are a few things to note about this definition. While value streams are traditionally thought of as shop floor tools, they also apply to administrative processes. It can be tricky to apply value stream maps to office environments, but the payoff is well worth the effort. It is just important to know that the tool works in services as well as with physical processes. I'd also like to point out that some definitions of value stream include the information flow as part of the value. I tend to believe that the information, unless it is actually the output of the process, is not part of the value. Rather, it just enables the value. For most businesses that have not yet started aggressively applying continuous improvement to its processes, the flow of value is rather impeded. You can think of it as a meandering stream. There are lots of pools and backwaters and rocks and sticks and other things blocking the flow, making it far less efficient than it could be. A value stream map is a tool that lets you figure out where all those obstacles are. The obvious goal is to remove those impediments and continuously streamline the flow. I just touched on an important concept, but I wanted to address it here again. As most people with a cursory understanding of VSMs know, they are very useful for tracking the value stream of a physical product. But they are also great when the product is information. Think of a loan process or an ordering process. There are a series of linked activities that move the information through time and space to satisfy a customer. Be careful about whether or not the activities are truly providing value, though, or if they are just a supporting process. For example, the materials management process is not a value stream, even though it contains a bunch of connected processes. One thing to keep in mind, though, is that value stream maps only work for repetitive processes. For example, it may be difficult to create a value stream map for a job shop. The flow of products through that system are simply too variable to get the full impact of a value stream map. That's not to say that a value stream map can't be useful in a mixed model line, though. It simply means that there has to be the potential for some consistency in flow. So now we talked a little bit about what a value stream is. Let's move on to what a value stream map is. A VSM is simply a snapshot view of how work flows through your system. This visual tool makes the opportunities for improvement jump out at you. So here is a sample of what a value stream map might look like. In this example, we look at Jimmy's lemonade stand. He does a pretty brisk business and now needs to streamline his process in order to keep meeting customer demand. Let's look at this example in more detail. The top section highlights how materials and information flow through the value stream. Information flow is generally shown in the top middle of the map. In this way, it is easy to connect information transfer between suppliers, customers, and the different processes within the company. Each process should also have an information box associated with it. These boxes not only show what you know, but also what you don't know. Generally speaking, when I look at a process, if the management team and the employees doing the process can't give me basic information, it acts as a red flag. You absolutely have to know how you're currently performing if you expect to get better. Speaking of people, I'd also like to point out that the value stream can be eye-opening to teams. Many times, people are unaware of where they fit into the big picture. This tool lets them see how their role fits into the value stream. Another big thing that this current state value stream map does is provide you with a backdrop upon which you can overlay your continuous improvement efforts. Seeing improvement opportunities visually on a VSM prevents you from taking a haphazard approach to Kaizen. Without the value stream map, it is easy to fall into the mode of a dog chasing a squirrel. It is very easy to get distracted and pulled away from what is important. This lack of coordinated effort is often called kamikaze Kaizen. While these unlinked projects can provide gains, these improvements are generally local in nature. They do little to improve the flow of the entire system. I do want to make an important distinction here. The term Kaizen is not used consistently throughout the Lean community. For some, it means a week-long improvement project. I, however, use the term Kaizen to describe any improvement activity, no matter how small. This would include daily improvements made by frontline employees. I don't recommend putting every single possible improvement on your value stream map. Focus on the larger projects that may require coordinated effort. Kaizen events, those week-long projects I mentioned earlier, fall into this category. Remember, a value stream map is a communication tool. One of the things you want to communicate is how resources should be used to get the biggest bang for the buck. Now that said, the bulk of daily improvements are not going to be linked directly to the value stream map. They should, however, still be prioritized based on KPIs, daily management, or countermeasures. The point I'm trying to make is that you don't want to limit individual improvement effort because it can't be seen directly on a value stream map. All of those little gains, as long as your team members understand the big picture, will add up. Just be sure that when you pull people away from their day-to-day efforts, you set them up for the biggest improvement opportunities possible. The final point of this slide is that when you put all of your improvement opportunities onto your current state value stream map, you are, in effect, creating a link between the present and the future state. This presentation will focus on creating that current state map, but I want you to view it with the end in mind. The purpose is not just to create a map. The point is to use the map to create a plan that will transform your current reality to that future vision.
Yes, let's see more about the value stream. Value stream map, we can see the whole process from supplier to the customer. Understanding of value stream, this is the scope. From their supplier, then our supplier, which is described here. Our piece, our site, and our customer. Value stream map, this is process box, this is supplier or customer. CT means cycle time. CO means changeover. Changeover means when we change from product A to product B in Toyota, the brand A, brand B, we call changeover. And uptime, scrap. How many shifts? How many scrap? This means inventory. Supermarket, shipment, push. This is physical pull, finished good to customer. FIFO, first in, first out. And the timeline is PLT, process lead time, and process time. Process lead time means the total time for the processing. PT means the pure process time without waiting, without delaying, without changeover, only cycle time. This is a sample, production control. This is supplier. This is customer. And there will be weekly schedule by MRP. This is a process, stamping, welding, assembly. This is cycle time, changeover. This cycle time takes only 1 second, changeover 1 hour. Uptime 85%. Only 1 second is for process time. This is process lead time, including all the waiting and other time together. So this is end of this class. Let's see next class. Thank you so much.